Hello and welcome to this new episode of Not So Fast. In this episode, what we are going to talk about is a very important notion called Fourier series. Now, Fourier series, you can think of them in mathematics as a way to analyze functions, and in particular periodic functions. And the way it works is it's as if you were able to decompose functions into their elementary constituents expressed in terms of harmonic functions, so functions with a very clear pitch, if you will. So let's see a little bit what the problem is that I want to address today. So first of all, what are Fourier series? Well, to talk about Fourier series, we need first to have a periodic function. So here, for example, you have, so the mouse should be visible here, so you have a semicircle, so that's an actual semicircle here, followed by a flat line at 0, and that is basically repeated over and over again over the entirety of the real line. Now, by definition, we call period the actual length of the elementary pattern, which is going to be repeated over and over again. One way to put it mathematically is simply to state that this is the smallest value, uppercase t, such that for any x on the real line, f of x plus t is equal to f of x. Okay, so that's basically the definition of it. Note, by the way, that's going to be important, that because this is true for any x, it follows that x plus t is also obviously equal to f of x, or even equals to f of x plus t, okay? Because, of course, x plus t is an allowed x, for example, okay? So what that means is that if t is a period, then 2t is going to be as well a period for the function, and so on and so forth. Okay, this is going to be important for what comes next. So what do we know of examples of periodic functions? Well, the typical one is basically the cosine function. So here I've plotted the cosine of 2 pi x over t, and essentially this is going to return this specific pattern. As you can see on the curve, on the graph here, you've got the green curve has basically one full peak, okay, and then one trough. And this is covering the entirety of the period t here, and this is going to be repeated over here on the graph. You can play the same game with the sine function, which is also of period t, so sine of 2 pi x over t is going to be a function of the period t we are looking at. So here there is exactly one peak and one trough in the actual pattern. And so you just repeat this over and over again. Okay? Now what happens is exactly, next is related to what I said before. And in particular, if you choose a period of oscillation of your cosine and sine functions, so here is t over 2 and t over 2 here, then you're going to see, it's a bit more complicated to see obviously, but you're going to see that there is a periodic pattern, but the pattern now that is going to be repeated over and over again actually contains 2 full peaks and 2 full troughs. Okay, and likewise for the sine function. So essentially, if you've got a cosine or a sine, then you can obtain something which is going to be of the right period t, as even if you divide the period of the sine and cosine by an integer n, that is posing basically no problem whatsoever, because the only thing this is going to do is that the pattern which is going to be replicated over and over again simply contains more and more trough and peaks. Okay, that's the only difference. So what that means is that in principle we can imagine that somehow a normal function which is periodic could be essentially written or decomposed as a sum of different cosine and sine function with different frequencies, just to ensure that the only thing that they have to do is to have the period t at the very least. Okay, and so in a sense what that means is that the function f of x can be written in this particular fashion. And that's, if you will, the elementary constituents I was mentioning earlier. We are going to deconstruct, if you will, a function into a sum of other elementary functions, which are here cosine and sine. So there is a constant term, which is a0, and then there is a sum here that ranges from 1 to plus infinity of some coefficients that are going to depend on the label n, and then cosine of 2 pi x t over n. So here we are going to sum of a cosine function of different frequencies, and in particular of increasing frequencies. Okay, and likewise here we sum up of sine functions of increasing frequencies, therefore decreasing period. Okay, so let's see how that works. So here I'm just stating that's how the decomposition works, but it turns out that you can work out as well what are these coefficients. So if you know the coefficients a0, an, and bn, therefore you know the entirety of the decomposition, if you will, of your function onto this elementary function. So you have unraveled everything there is to unravel with regards to the behavior of that function from a periodic function standpoint. So this is how that works. The a0 is actually the integral of a one period of f of x dx. Here I've chosen 0 to t, but to be honest, because it's an infinitely going function from minus infinity to plus infinity over the entire real line, you could take it basically on over any interval that is simply of length 1 period. Okay, so that's for a0. Now the tricky bit with Fourier series is that an is the same thing almost, except that you do integrate over 1 period, but then there is a factor 2 here. So this is something to be careful about. And you basically take the integral of f of x with cosine of the corresponding frequency here, which is t over n. And likewise, bn is 2 over t, integral from 0 to t, f of x sine of 2 pi x over t over n. Okay, so that's how that works. Now, for the example I'm just providing, actually these integrals are quite complicated to evaluate. So I've evaluated them numerically using Mathematica, and so here what I'm showing is simply the first order. So a0, then plus a1 cosine 2 pi x over t plus b1 sine 2 pi x over t. And I'm getting an approximation of the initial curve, which you see resembles just like a sine function, really. I mean, there's not much difference yet. Now, if you actually add to the fourth order, so essentially you add frequencies t over 2, t over 3, and t over 4, then you actually get something that starts to look like a bit better with regards to where we started. And then by the 40th level or degree, then you get something which is essentially indistinguishable. There are some things that are going on at the corners here, which are quite difficult to capture, but otherwise we basically got it fully. Okay, so essentially what matters is that this particular decomposition onto elementary functions, which are cosine and sine, again, you can imagine them to some extent as being a sort of atoms of that function, and then you try to see how these atoms are kind of put together in order to give rise to that function. Now, the thing here is that it's like in chemistry, this function is actually uniquely characterized by this particular thing. And so I think that's quite important. It's unique, as long as you have a periodic function, is going to have a uniquely characterized Fourier series expansion, okay, which is this thing. Now, what is the problem that I want to talk about? The problem has to do with questions like this, whereby basically a question is provided where you're given a function of a finite interval, and what you have to do is actually find the Fourier series of this particular function. And that we are going to see why that's an issue. So let's take an example that everybody can actually calculate by hand, or at least if you try long enough. So here I take a triangle function and I give you the exact value of that function. So it's 2x for x that is from 0 to a half, and then 2 minus 2x for x that is between a half and 1. Okay, so here this is going to reach 1, and this is between 0 and 1. And what we may ask here is, okay, find the Fourier series of g of x. Now the problem is that this is not a periodic function, so this particular object or function actually doesn't have a Fourier series. That's kind of the problem. We said earlier that essentially the goal is to express periodic functions in terms of other periodic functions which have the same period, or at least that contain this period as part of this repetition pattern. So the way it works is that what you need to do is to create what is called a periodic extension that I'm going to call GP of x of g of x. And once you have this periodic extension, then you find the Fourier series of GP of x. So, for example, this is a particular periodic extension of this particular function. Here, of course, you need to imagine that this is continuing on and on and on and on, etc. Now, the period of this particular periodic extension is 1. So 1, 1, so you've got a repetition of the initial function of the pattern essentially kind of once. That's the smallest, period that you get here. Okay, so what do we do then? Well, you can actually calculate then, given this, you can calculate the corresponding values. So you will find actually that first of all the period is 1, so it's 1 over n instead of t over n, and you will find that a0 is a half, an has this somewhat complicated looking expression which is 2 over pi squared n squared minus 1 to the n minus 1. That's for n different from 0, otherwise you're kind of in trouble here. And then bn is actually 0 in this particular case for all possible n values. So that's quite convenient, to be honest. So let's see how that looks. So here, for example, I'm putting together the first order. So essentially that's a half minus 4 over pi squared cosine of 2 pi x. That's for n is equal to 1. Now, for n is equal to 3, then you can play along if you want and try to plot this on your favorite softwares, maybe on Wolfram Alpha. So you get an approximation which you see is not too bad. It starts to resemble things here. But then, by the 9th level, you get something that works really well. Now, there is some yellow that remains from the function, but it may have to do with the way simply the software I'm using is overlaying the two functions. What you can see basically is that already by, that's not the 9th order, that's the 19th order, and the only thing I've noticed here is basically that this works every odd number. So you get something which is going to be 0 otherwise. Okay, so that's for one particular series expansion that works very well, as you can see. Here I've stopped again at n is equal to 19. Of course, you can continue further as well. Now, the issue is that, again, if we start from these very steps here, then we have more than one manner to obtain a periodic extension of g of x. For example, let's call g tilde p of x this particular periodic extension of that function. So here I've got the initial function, then I put a flat line which is at 0 from 1 to 2. So here this is a number 2, and then you repeat again. So the pattern that is from 0 to 2 is being repeated over and over again on the real line. Okay, so in this particular case, it means that I need to deal with a Fourier series expansion where the fundamental period t is actually at 2 instead of 1. Okay, so this is going to change a lot of things. So in particular, a0 in that case, so here this is 1 over n, but I've removed the 2 here. So it used to be 2 pi x over 2 over n, okay? So here you've got a0 is equal to 1/4, and here you've got 2 over pi squared n squared, and you've got this quite complicated expression here. 2 cosine n pi over 2 minus cosine n pi minus 1, and again for n different from 0. And here, likewise, for n different from 0, you've got 4 divided by pi squared n squared sine n pi over 2. So these are different. Bn now is not 0 anymore. Here a0 is 1/4, and you've got this quite complicated expression here. Now, we can play the same game as before and try to plot how that looks. So I'm plotting the function we had here. And then I'm plotting just the first, actually here, 2 orders. So it's 1/4 plus 4 over pi squared sine pi x minus 2 over pi squared cosine 2 pi x. Okay. Now, if I increase the order, so here this is n is equal to 6, I already need to write an actual sum because it's quite, it becomes very, very cumbersome very fast. Okay. So that's how this works. The only thing that what these indices mean here is basically that I've noticed that the cosine part is only looking at the even numbers for n, and likewise I've noticed that the sine part only looks or is non-zero only for the parts where n is actually odd. And so that's what these sums actually represent. And so at the end of the day, for the order 19th, I get this particular fit to the initial curve. So now what happens is that if we put these things together, what we see is that we've got 2 different functions, okay? But if we actually look at this particular window, then they are indistinguishable from each other, and each are actually going to represent perfectly this piece of that function between 0 and 1. So essentially it shows that these things are not unique. Okay, so if you have a function which is expressed along a finite interval that is defined on a finite interval, then there is no unique way of expressing it in terms of a Fourier series. In fact, there are infinitely many ways to do so, and it depends simply on how you choose to do your periodic expansion of that function. And obviously here the limit is your imagination. So sometimes people think that what the Fourier series is actually doing is to somehow create out of thin air an implicit kind of function with like some periodicity and so on. But that's not what the Fourier series does, okay? You take the Fourier series, which is again some kind of atomic decomposition of a function. You actually look at it once you already know it, it's to be periodic. And this atomic decomposition is going to crucially depend on the period that you've chosen in your periodic expansion. Okay, so that's really the crucial part. Now, in essence, the fact that there is no unique decomposition of a finite function, so a function defined on a finite interval, what it means is that essentially you can't consider or view cosine and sine function as being, at least with a sum of discrete or integer frequencies and so on. You can't actually consider that as being some kind of atomic versions or ingredients of that function. They are not enough at all to characterize that. Now, that doesn't mean that you can't characterize your function with cosine and sine. This is actually possible, but in that case, what that means is that you need to use all possible frequencies. And in fact, this is called the Fourier transform, and what you need to do is to use an infinite and, in fact, uncountably infinite amount of frequencies in order to characterize uniquely a function which is defined on a finite interval. Okay, so please, in terms of the key message here, is that if you want to use Fourier series, then you need to use you need to really consider this idea that this has to do with a specific periodic extension you would have chosen, and therefore you cannot really extract meaning from the Fourier series expansion of a function defined on a finite interval. If this is meaning or this kind of atomic decomposition of a function that you're looking for, then you would be better off to look at the Fourier transform instead. So that's it. So please be careful. So at best you can find a Fourier series. Usually you try to find the simplest one possible for your specific case. So that's it. So I hope you enjoyed it. If you've got any questions, please let me know in the comment section.